Hello and welcome. In this video, we're going to take a look at the common ways to validate our models so that we have greater confidence they will be generating reliable predictions on new data and for real-world applications. So in general, for supervised learning, whether we're predicting labels in a classification task or continuous values in a regression task, we are going to be using some form of training and testing to build effective and reliable models. And training is really where all the magic happens. We feed the model data, and the models understand the underlying patterns or learn the underlying patterns and tunes its internal parameters so that you minimize errors in prediction mode. And what's the goal of all of this? The goal of all of this is to get the model to understand the data well enough to make predictions on new, unseen data. Or in other words, you want to teach the model to generalize to new data. So in order to construct a model that's reliable and generalizable to new data, we need to also test our trained models. So typically this involves taking your trained model and putting it to test a separate data set it's never seen before. And so this crucial step reveals how well the model generalizes to new data. And it also helps us identify problems like overfitting, where the model performs fantastic on training data, but fails miserably on new data. You can imagine this happening with regression tasks, where the model might have very close to zero errors on the training data, but then when you want to make predictions on some holdout data set, the errors are substantially large. Alternatively, we can also have underfitting, where the model does not really capture the input-output relationships at all. And it turns out that both the idea of training a model and testing a model is absolutely essential. As I mentioned earlier, training allows the model to learn, and testing validates that learning. It ensures reliable predictions or generalization to new data. And testing also helps us to detect whether we are biased in some form, because we don't want our model to be too specific to the training data and therefore unreliable. So it is a very, very crucial step before you deploy any model, which gives us, and testing gives us that confidence that we will obtain reliable predictions in real world applications. So what we're going to be doing next is looking at various ways to validate these models, and we'll start with the regression problem. Over here, we have a bivariate data set. We have one target variable plotted on the y-axis and the input feature on the x-axis, and there are about 9 data points over here. And the question we're asking ourselves is, which model best expresses this relationship? And we have multiple choices for models, but let's just consider 3 different models. One of the models is just a straight line. The other one is a quadratic model. And the third one is a piecewise linear non-parametric regression model. And the question we want to ask ourselves is, given these 3 models, which of these best captures the trends in the data and is also able to generalize to new data points? So one way of doing this is going through a procedure of training and testing, which is what we're going to be discussing next. So what training and testing involves is to split the data set, the entire data set, randomly into a training block and a test block. And this should be done entirely randomly. Typically, the testing data might have 15% of the data or 20% or 30%. And the size of our test data set largely depends on how much data we have available to us and what kind of model complexity we are testing. But a good rule of thumb is usually 80% for training and 20% for testing. So this is pictorially depicted in this panel over here, where I have some points colored in blue, which is my training data set, and some points in red open circles, which is my test data set. So what I'm going to be demonstrating next is that I'm going to fit a model to these blue points, and the model is going to learn from the input-output relationship. And then, given that model, I'm going to make predictions, and I'm going to compare the predictions it makes with respect to the test data. So let's go ahead and see how that works. So here in the case of a straight line linear regression model, what I have is this green line over here, which best fits the blue points. And while it does capture the large scale trend in the data, we also want to see if it can generalize to new data. So for a given, I'm going to compare this model performance against my test data. So for a given value of X, the prediction that the model makes is located along the straight line. But for that same value of X, the actual data is where the open circle lies. And so you can see there's quite a bit of discrepancy or error between the model prediction and the data point. If you look at the other test data point, you can see that there's some discrepancy there as well. And looking at the third data point, there's a smaller discrepancy. But overall, you can see that there are some errors associated with the test when the model was applied to the test data. And let's just say that the mean squared error has some value of 2.4, for instance. So we're going to perform this task and keep it aside. And next, we're going to try a different model. So this time, we're going to try a quadratic regression model. We're going to fit a quadratic equation to the blue points. And that's denoted by this green line over here, or the green curve over here. And now, for every value within our test data set, we are going to make predictions and see how far are our predictions from the test data. So you can see that compared to the test data or the observations, we do have some discrepancies as well. There are some errors between the model prediction and the actual data. So we compute the mean squared error, and in this case, it happens to be 0.9, and we keep that aside. So the third model available to us is the piecewise linear non-parametric regression model. So we essentially just connect all the blue points, which is our training data set. And you can see that it fits all of the blue points perfectly because that's what it's designed to do. But then we take this model and see how well it performs on the test data set. And you can see that the errors are quite large again when applied to the test data set. And just for argument, let's just say the mean squared error was 2.2. And so in this specific example, if you had to make a choice about a specific model that best fits the trends in the data and also does well with new data, then your choice would be the quadratic model because it captured the trends given by the blue points and did reasonably well against the test data in comparison to the straight line and the piecewise linear regression model. And training and testing, this method of training and testing is widely used. There are, however, some disadvantages to this. One of the disadvantages is that we are selecting our test data set entirely randomly, which means that we are not selecting the bottom 20% of our data or the largest 20% of our data or the middle 20% of our data. We're selecting randomly from across the entire data set. In other words, we want our training data and our test data to contain the same model diversity. That's what we would like to have. But because we're doing things randomly, it's entirely possible that our test data set may be biased in some fashion. Just like you can win the lottery entirely randomly, it's entirely possible, and that's an unlikely event. It's also possible that you may select a biased test data set. And if you did something like that, then the concept of training and testing breaks apart because you are training on data with a certain kind of distribution or diversity, and you're testing it against a completely different data set with a completely different diversity or distribution. So just to give you an example, if you had a bivariate data set, if your test data contained just the 20 largest 20% of the data, and your training data set contained 80% of the smallest values of the input features, then no matter what you do, it's highly unlikely that uh, uh, even very sophisticated models would do well against your test data set. So while training and testing is useful, and while it's also unlikely that we would be generating a very biased test set, that possibility exists. So we want to explore other options. So one of the things that we could potentially do is something called leave one out cross-validation or k-fold cross-validation. But before we do that, let's watch a video illustrating training and testing in action. So in this case, I have my training data, which is shown in blue, and you have about 10 or 11 points. I have my target variable along the y-axis, and I have my input variable along the x-axis. And this is purely for illustration purposes. You can have a multivariate input, and you can have multiple outputs as well. And we also do this for classification tasks, but I'm illustrating this with a regression task. And so now, out of the entire data set, I'm going to randomly select these 5 points to be my test data. So the entire data set is all of these 14 or 15 points, and my test data is made up of these randomly selected 5 points. Okay, so first things first, I'm going to fit this with a model of some sorts. And in this case, it happens to be a straight line. And for this straight line, it best fits our blue dots. And then when I introduce my test data, I want to see what's the discrepancy between my model predictions and my data. So for a value of 0.5, my model prediction is given by the red dot, whereas my data is given by the yellow dot. So there's quite a bit of discrepancy over here, or some amount of error, and some amount of error over here. So we compute the error and keep this model aside. And then we try a slightly different model. And this time around, this is a third order polynomial. And you can see that the data now, because you have the help of a sine or the third order polynomial, you can see that the data is spread out along a sine curve. And this third order polynomial is fit to the training data. It's fit to the blue points. And you can see that it does a very good job of capturing the trends within the data set. Now, the question is this good enough for us? So we're going to now introduce the test data and see how well the model does against the test data. So you can again compute the errors between the model predictions and the test data and keep this model aside. Now, the third order model polynomial did really well. So, so why not try something more complex? Why don't we try a ninth order polynomial or a 10th order polynomial? And that's exactly what we're doing over here. I've fit the blue points, my training data, with a 10th order polynomial. And you can see that it matches my training data perfectly. In fact, the discrepancies between the training data and what my model is telling me is exactly zero. Well, let's just see how this model does against the test data. So what I'm going to do is compute the errors with respect to the test data, and I'm going to keep this model aside. And so you can see that we tried three different models. One was a straight line. The second one was a quadratic, was a third order polynomial. And the third one was a ninth order polynomial. In the case of the first one, it did not match the data too well. It was underfitting my model. It was also not doing too well against my test data. The last model, which was my ninth order polynomial, was matching the training data perfectly, but it had a large amount of errors with respect to the test data. And that's a symptom of overfitting. We overfit our training data, and the model can't generalize well to new data. That's exactly what overfitting is. And the model that we tried uh, uh, in between, which was the third order polynomial, had the right balance of capturing the trends in the data while also not being too far removed from the test data. And that's how you can select a model or choose the appropriate model complexity when you have multiple models to choose from. So that's training and testing. So next, we're going to see what is leave one out cross-validation. Again, just keep in mind the reason why we're trying other approaches to validate models is because it's entirely possible that we might select a test data set that's biased. So the idea behind leave one out cross-validation is, again, the same as training and testing, except that this time around, we are going to select only one point to be my test data point. And we are going to fit a model to the remaining data. So over here, this picture illustrates what I mean. I have the points in black, which is my training data, and I have this one open circle, which is my test data. So I fit a model to my training data set and then see how well it does against my test data set. And you can see that there is some error associated with this prediction. And this is fine, but why did I select this point? Why don't I select the other points to be my test data? And that, in short, is really what leave one out cross validation is all about. I'm going to cycle through all of the points, and in each iteration, a different point becomes your test data, while you fit a model to the remaining 8 or 9 points. And that's illustrated in this panel on the left, where we're seeing different slopes because in each instance, we are fitting a straight line model to a different data and validating it against a different test point. In the second panel, I'm fitting the model to 8 points over here and testing it against one of the test data point. The third time around, my test point is here. The sixth time, my test point is over here. And the ninth time, my test point is over here. And I'm going to have 9 different models And the average error associated with each one of these 9 fits is going to give me an idea of how well my straight line linear regression model is doing with this data set. So I'm going to keep that aside and then try a different model. So I'm going to go with the quadratic model, and I try the quadratic model. Given that I have 9 points, I'm going to have 9 different test points occurring in sequence and 9 different training data sets and 9 different models. And you can see that happening in these panels over here. If I focus on this panel over here, you can see that I have the 8 training points to which I fit the green curve, and I test it against this red data point. So I take the average error associated with this entire set of experiments, and I keep that aside. Then I try the linear piecewise regression model, and that's going to give me some average error over all of the 9 points. And I keep that aside. And I see which of these 3 different models, or if I'm testing more models, which of these multiple different models results in the least average error when I apply leave one out cross-validation. So in this case, you can see that we are not leaving out any data point, and you're testing it against every single data point. So really, you are seeing how well a specified model can capture the diversity in your data. And this is leave one out cross-validation. And of course, you can imagine that this would be prohibitively expensive to apply for very large data sets. But if you had only 10 points or 15 points, which is quite routine, then we might consider leave one out cross-validation. And let's see that in action. So again, we'll take an example of regression. So I have my target variable on the y-axis. I have my input feature on the x-axis, and I have some shape over here. This is my data set. I choose one of the points to be my test point. And that's my test point. And the remaining points are my training points. So I fit a model to my training points. In this case, I've chosen it to be a quadratic model. And I measure the discrepancy with respect to the test data point and keep that aside. Then I choose another test point, fit a model to the remaining points, and see what's the discrepancy with respect to the test point. And I repeat this for all of the all of the 9 points that are seen in this specific data set. So you can imagine that we're doing this 9 times, and each time I get some testing error, and I average out the errors across all of these 9 different models. And I'm going to speed up this video. And this is for one single model. Of course, the reason why we're using any kind of validation method is because we want to choose amongst many different models. So I'm going to repeat this whole process for maybe some other polynomial or some other function and see which of these gives me the best fit on my data. And as I mentioned earlier, leave one out cross-validation is perfect for small data sets. Okay, what if you had large data sets and you want to avoid any potential bias that might occur because of selecting just one test data set? So then you can imagine that you may want to choose 3 different test data sets or 6 different test data sets or 5 different test data sets. Well, how is that going to be possible? In principle, it's pretty straightforward. So imagine that we had our data set. I'm going to randomly break it up into 3 different folds or 3 different buckets. I'm going to call it fold 1, fold 2, and fold 3. So for three-fold cross-validation, we will have three folds in my data set. I'm going to construct a model that's going to be trained on fold 2 and fold 3 in combination and test it against fold 1. Then I'm going to take another model, fit it on or train it on fold 1 and fold 3 and test it on fold 2. Then I take a third model, train it on fold 1 and fold 2 and test it against fold 3. So I repeat this across models of different complexity and see which of the models does better on average over all of these three folds. We'll see that in action in the panels below, but before I go down, let's look at this image over here. You can see that some points are colored blue, some points are colored green, and some points are colored red. So each of these different colors represents different randomly selected folds. We want to randomly select our folds. It's not the bottom 30% of the data or the middle 30% or the top 30% of our data. It's entirely randomly selected. So first, I'm going to try a simple linear regression straight line fit. I'm going to fit it to the training data, which is my blue and green points, and I'm going to test it against the red points. So I'm going to get some model prediction error. Next, I'm going to fit another straight line, but this time I'm going to fit it to the blue points and the red points. So I'm going to switch the folds. I'm going to test it on the blue points or train it on the blue points and the red points and test it against the green points, which is what I'm doing over here. And for the third model, because I have three folds, I'm going to train it on the red points and the green points and test it against the blue points. So from the first model, we're going to get some error. From the second model, we'll get another error. And from the third model, we'll get some other error. And now you can compute the average error associated with three-fold cross-validation when you're attempting to fit a straight line to the data. We're going to repeat this process with a quadratic model. And with the quadratic model, we again fit three different models because there are three different folds we are training against. And we get an average error with respect to the test data over all of those three folds of 1.1 in comparison to what I got with a straight line model, and the value is 2. I repeat this with my piecewise linear regression model. And again, you can see three models over here. And each one of these three models is going to have some error associated with predictions against the test data. I'm going to average out the errors, and the average error is 2.93. And given this information, the one I'm going to be choosing is my quadratic regression model, simply because on average, the predictions associated with the quadratic regression model are the least. Now, this is important because we have minimized the bias with respect to selecting my test data. It's very unlikely that when I split my data set up into three different folds, it's very unlikely that I would be biased in some way. If I go to 5 different folds where each fold has a randomly selected 20% of the data, it's unlikely that in all of the 5 folds, I would be biased in some fashion. And so you can see that k-fold cross-validation is what's the most commonly employed testing method to validate models or choose the appropriate model complexity. Of course, keep in mind that when we are evaluating a model, we're not only looking at how the model does on average, we're also going to compare this model performance on average with respect to the individual errors as well. And I'll explain that a little bit more when we watch the video related to leave one out cross-validation. This is a regression example again. I have some training data and I have some test data. So I first fit a straight line linear regression model to the data, and I tested on fold one. So these yellow points are my fold one data, and the blue points are my fold two and fold three data in combination. This is going to result in some error. I keep that aside. Now I take fold two and train my data on fold one and fold three and test it against fold two. And then I repeat this process where I train the model on fold one and fold two and then test it on fold three. And with that, I'm done with the linear regression model. I'm going to try a third order polynomial next. With the same folds, I train it on fold one and fold two. Sorry, on fold two and fold three and test it on fold one. Then I train it on fold one and fold three and test it on fold two. Then I train it on fold one and fold two and test it on fold three. And I get three different errors, and I'm going to average out those errors and keep that aside. Now I'm going to try a ninth order polynomial. So I'm going to fit it to fold two and fold three and test it against fold one. And you can see that the ninth order polynomial overfits the training data, but does really poorly against the test data. And finally, I'm going to test it against fold three. And finally, when I compare the results, I'm going to see what happens with the linear model, the third order polynomial, and the ninth order polynomial fit. So let's look at the linear model. For each fold, the error was approximately 3, and on average, the error is approximately 3. It's 3.1, 3.0, and 3.2. Let's look at the third order polynomial. The error with respect to testing on the first fold was 1.2. Testing against the second fold is 1.1. Testing against the third fold is 1.4 with an average of 1.23. With the ninth order polynomial, testing against the first fold was the error was 14.6. Against the second fold, the errors were pretty small. It was about 3.4. And with testing against fold three, our errors are 5.6 with an average error of approximately 8. So few things to point out over here. In the linear model, the average error and the difference or the standard deviation or the variation in the errors across each one of the folds was very minimal. What do I mean by that? The average was 3.1, and you can see that pretty much across fold one, fold two, and fold three, the errors were about 3.1, 3.2, and they weren't too large or too small. If you look at the third order polynomial, the errors were pretty much the same around 1.2 or 1.3. The variability across different folds was very small. Let's look at the ninth order polynomial. You can see that against fold one, the error was as much as 15. Against fold two, the errors were really small and approached a value of about 3. And what this is telling us is that the model is really overfitting the data. It worked really well when I trained it on fold 1 and fold 3, but when I and tested it on fold 2, I got an error of only 3.4. And if you had just gone away with this one test point, you would be somewhat happy with this model. But now if I change up my test data set and train it on fold 2 and fold 3 and test it against fold 1, my errors are as high as 15. And so you can see that the ninth order polynomial is not generalizing to new data very well. So this is the nice thing about cross-validation or k-fold cross-validation. It not only tells you what the model is doing on average, it tells you what the model is doing individually across each one of the folds. And that's giving you information on whether the model is generalizing well to new data. In essence, this is what I wanted to discuss in this video. We started off with the idea behind validating a model. We discussed training and testing, and then we moved on to leave one out cross-validation, which is really important when you have smaller data sets. And finally, when you have large data sets, something that you may want to use is k-fold cross-validation, where k represents the number of folds. And typically, a rule of thumb is we try at least 5 to 10-fold cross-validation.